So this question we're looking at 13a. So it says a projectile is shot straight up in the air at a velocity of 20 meters per second. So this is going to be, I'm going to write this in as dy by dt is equal to 25 meters per second. An observer viewing the projectile is 100 meters away. And at what rate is the angle for the observer changing when the object is 75 meters in the air? Okay, so I'm trying to find the angle, the rate of the angle changing. So that's d theta by dt. And I'm just going to sketch this diagram. So I've got a person that's 100 meters away. There's my 100 meters. There's my theta. There's my y. Okay, and at the instant that this is equal to 75 meters, I want to know how fast that angle is changing. Okay, so there's my scenario. Basically, I need to connect the 100 meters, or the x, the y, and the theta. Okay, so how do I connect vertical, horizontal with the angle? Well, I have vertical and horizontal represent slope, so I can connect it to the tan ratio. So that's the first thing I'm going to do. I'm going to identify the quantities involved. Then I need to figure out the equation that connects horizontal, vertical, horizontal, and the angle. And that's going to be connected through this tan theta is equal to y over x. Okay. Now, we're going to differentiate this with respect to x. Now, in this case here, the x, since it's not changing, we don't need to differentiate it. So it's just going to change to 100. So this even more simplifies the expression. So I'm going to differentiate this. I could generate d theta by dt, and I'm going to generate dy by dt in this expression. So I've identified my variables. I've written an expression to connect the variables. I'm going to now differentiate with respect to time. So this becomes secant squared theta. So I differentiated the tan, but now I have to apply the chain rule, d theta by dt. Okay, so that's going to be the d theta by dt that I'm looking for, is equal to the slope on that expression is going to be 1 over 100. And then since I differentiated y, I need to attach y prime, which I'm just going to write as dy by dt. Okay, so this is applying the chain rule because y is itself an embedded function of t, and that generates my dy by dt. So there it is. I have everything I need. So I just have to fill in what I have here. Okay, so I have, let's see, I need my theta. Ooh, I don't have theta. However, I do have this picture to work out theta. I'm calculating d theta by dt. I have dy by dt is 25 meters. So then what's left is then I just have to figure out what the theta is when I'm calculating this. Well, since I have 75 over 100, I can say that tan theta is 75 over 100 to get theta, and then I can calculate theta that way. But more importantly, actually, although I want theta, really I want secant squared theta. I want secant theta, and I can actually get secant theta without actually solving for the angle. So that would be much easier. So I'm going to do that. So to get the expression for secant theta, I'm going to end up having to solve for the third side. So 100 squared minus or plus 75 squared. So using my calculator, 100 squared plus 75 squared. That's going to give me 15,625. I'm going to square root that, and I get a length here, hypotenuse length of 125. Well, based on my secant ratio, which again, I'm avoiding finding the theta because I don't have to, because I really just need the secant ratio. The secant ratio is going to be 1 hypotenuse over adjacent. Okay, so that simplifies to 5 over 4. So instead of solving for theta, which I just as well could have, I'm just going to replace the secant squared theta with 5 over 4 squared. I have my d theta by dt, which I'm solving for. It's equal to 1 over 100, and it's times by, I've been given dy by dt as 25 meters per second, okay, going up, so it's positive. So I'm going to solve for this. Okay, so I'm going to do it down here. So I end up with 25 over 16 d theta by dt is equal to, this works out to be 1 over 4 meters per second. Okay, and so this is, these units are going to end up canceling out. So I end up with d theta by dt. Okay, so d theta by dt is equal to 1 over 4. I'm going to times by 16, divide by 25 on both sides. Some things cancel out. So my d theta by dt, and radians have no units, by the way, is going to end up being 4 over 25 radians per second. Okay, so we could just, although the units cancel out, the radians are when the units cancel out. So there's my solution to the angular change. So that's going to be rotating upward at a rate of about 0.16 radians per second when I work out the decimal value of that fraction.